Hello students, in this video lecture series we will discuss all these cases. We will draw shear force diagram and bending moment diagram for each case. In previous videos we have solved this case, this one, this one, this one and this one. In this video we will solve case simply supported beam subjected to uniformly varying load over entire span. The shear force is positive if it tends to move left portion upward relative to right portion. Suppose this is a beam and this is left part, this is right part. On left part I am applying force upward like this. So we can see here again we are applying force like this. So this is left part on which force is applying upward and this is the right part on which force is applying downward. If this is the case, it is a positive shear force. Again we will see the shear force is positive if it tends to move left portion, this is the left portion, upward relative to right portion. This is another case which is opposite of this. If this case happens, then it is a negative shear force. The bending moment is positive if it tries to sag the beam. If left portion of the beam is considered positive movement, works out to be clockwise. So this is a section and it is the left part and bending moment direction is this side, clockwise, and we are seeing this is a beam which is sagging. If this case happens, it is a positive bending moment or sagging bending moment. Again we will see the bending moment is positive if it tries to sag the beam. If it tries to sag the beam, if left portion of the beam is considered positive movement, works out to be clockwise. So we are seeing this is clockwise movement and we are taking it as positive. If it is opposite of this one, it is hogging. So we will see it is negative bending moment because at the left portion bending moment is anti-clockwise. This is positive bending moment in which beam is sagging. This is negative bending moment in which beam is hogging. This is a question. AB is a simply supported beam at point A and B and load is uniformly varying from point A to point B. At point A load is 0 and at point B is W per unit length. So first we will calculate reaction RA and RB. For this we will convert this load, triangular load, into the point load. So AB is a simply supported beam. You have to find out RA and RB, and this is the point load which is half W into L. Area of the triangle is half, this is W base into length. So it is half WL. Now this load will act at a distance of L by 3 from this end. Total length is L and from this portion load will act at a distance of L by 3. So this is a distance L by 3. Now we will apply the condition of equilibrium. So these are the coplanar forces. Conditions are sum of horizontal force is 0, sum of vertical force is 0 and sum of moments is 0. As there is no horizontal force, so we will skip this portion. Now we are coming to this equation Fy. So first is Ra, which is upward, Ra, then half Wl is downward, half Wl, and third is Rb, which is upward, it is positive. And the sum should be equal to 0. This is one equation. And third is movement. We will take movement about any point. We are taking movement about point A, and the direction is movement in anti-clockwise direction is positive, and we are taking movement at about point A. So movement is force into perpendicular distance. This is a force and this is a distance, AC is a distance. So force into perpendicular distance, and it will rotate beam like this in clockwise direction. So movement will be negative, half Wl, this is the force and this is the distance, into 2L by 3. It is negative because it is in clockwise direction, and our sign symbol is in anti-clockwise direction, it is positive. Then second force Rb, and movement from point A is, this is the distance, total distance is L. So it will rotate in this direction. So it is anti-clockwise. Force is Rb into distance is L, and the sum of movement should be equal to 0. This is 0. So from this equation we can find out Rb into L equal to half Wl into 2L upon 3. This will come to this side. So we will cancel L, and 2 and 2, this is cancelled. So Rb is Wl by 3. So we know Rb is Wl by 3. So we will keep Rb here and we will find out Ra. Ra minus Wl. Rb is Wl by 3 plus Wl by 3 equal to 0. So Ra equal to Wl by 3, it will be minus, and it will be plus half Wl. So Wl is common, minus 1 by 3 plus 1 by 2 equal to Wl. LCM is 6 minus 2 plus 3. So it is Wl by 6. Ra is Wl by 6 and Rb is Wl by 3. Rb is Wl by 3. After calculating reaction at point A and point B, we will write the shear force equation. First, we will take section between AB. which is y dash, and the distance of this section from free end is x. So, we will see towards the left of this section. So, first we will find out this distance. This is A, B, C. We are saying these points is D, E. So, there are two triangles A, D, E and A, B, C. We will use similar triangles and we will find out this length. AD upon AB equal to AD upon CB. AD upon CB. AD is x, AB is L, AD we have to find out, and CB is W. So, ED equal to W x upon L. Shear force equation. We will see towards the left of this section there is one force Ra which is upward. So, it will be positive W L upon 6, it is upward, that is why it is positive, and there is one more force which is this triangle. So, total force is half base into height, and this force will act downward, that is why it will be negative. Half ED, this is base which is Wx by L, Wx upon L into x, height. This is the area of the triangle. So, this is general equation of shear force. Shear force at x equal to 0 we will slide this section to this side. So, x will reduce. So, we will keep x equal to 0 in this general equation, shear force. This is the shear force general equation. So, we will get W L upon 6 and shear force at x equal to L. We will slide this section to this side. So, x will increase and x will become equal to L. So, this is general equation. We will keep x equal to L in this equation. W L by 6 minus half W L into L upon L. It will cancel L. So, it is W L is common, it is 1 by 6 minus 1 by 2 equal to LCM is 6. So, this is 1 minus 3 and it is WL. So, it will become minus 2 WL upon 6 equal to minus WL by 3. So, shear force at point B is minus WL by 3 and we are seeing here this equation, this general equation. Here it is coming x square. So, it is parabolic variation, This is general equation of the shear force and we are seeing here it is coming x square. So, it is a parabolic variation and we have calculated at point A shear force is WL by 6, at point B or x equal to L shear force is minus WL by 3. So, it is a parabolic variation. So, one side is positive, we are saying it is positive, it is negative, it means there will be some point at which shear force will be 0. So, this is a general equation, we will keep shear force equal to 0 here and we will find out the value of x. So, it is coming 0.577 L. So, from here it is 0.577 L at which shear force is 0. Bending moment equation. Bending moment is the force into perpendicular distance. So, we will see towards the left of this section there is one force RA, it is upward force into perpendicular distance from the section is x. So, bending moment is RA into x. At the left of this section there is a triangular force. So, triangular force is half, we have already calculated it, W x by L into x. This is force into perpendicular distance. So, this is a triangle, we will see here A D, this is a triangle A D E. So, we will convert it into the point load, this is the point load and force is, this force is, we have written here, this is the force, it is downward minus half W x square by L and this point load will act at a distance of this. So, this distance is, we know total distance is x. So, it will be x by 3 because it is the base of the triangle and CG will act at a distance of x by 3. So, it will be x upon 3. So, for this triangle ADE we will convert it into the point load and the point load will act at a distance of x upon 3 from section. So, we will multiply here by x upon 3. Now, I will rub this one. So, bending moment is WL by 6 x minus W x cube upon 6 L. So, this is the equation, same equation, bending moment at x equal to 0. We will slide this section to this side. So, x will reduce. So, at x equal to 0, we will keep x equal to 0 in this equation, bending moment is 0 and bending moment at x equal to L. We will slide this section to this side. So, x will increase and when this section will come to this side at point B, so x will become equal to L. So, we will keep x equal to L in this equation, W L square by 6 minus W L square by 6 equal to 0. So, bending moment at x equal to 0 is 0 and bending moment at x equal to L is 0. We will see this equation, here it is coming x cube. So, it is cubic variation. We have find out shear force is 0 at a distance of 0.577 L. So, bending moment will be maximum at this distance. This is bending moment equation. We will keep x equal to 0.577 L. So, bending moment is at x equal to 0.577 L equal to, it will come out 0.06415 W L square, which is maximum bending moment. Where shear force is 0, we will get the maximum bending moment. So, bending moment at point A or x equal to 0 is 0 and bending moment at point B or x equal to L is 0. Bending moment maximum value is this one, which is at a distance of 0.577 L. So, it is a cubic variation. So, slope will be like this. So, this was the numerical on simply supported beam subjected to uniformly varying load over entire span. In next video, we will solve simply supported beam subjected to an external movement. Thank you.